What up, Cam? How we doing? Just want to go over some things real quick. We learned about polarity today. So, we learned about two things, polar bonds and polar molecules. It's important that you know what both of those are independently and how they work together. First off, water. Water is amazing. Because water is polar, we have so many cool things. Cup of noodles, bagels, cream of wheat, pasta, hard-boiled eggs, Chef Boyardee, raviolis, Red Baron pizza, Hot Pockets, oatmeal, SpaghettiOs. So water's amazing. This is why you can do all those cool things or eat all those cool things, because it's polar and it's got a boiling point of 100 degrees Celsius. Why does it have this? Well, two major things. It's got polar bonds and it's a polar molecule. So what's the dealio with those? Polar bonds are like a tug of war, where one atom or person is winning and the other one is hanging on for dear life, but has pretty much lost. So for O and H, if we treat the middle as like the center of the rope, we're gonna see oxygen winning that tug of war. It's like going off the screen. Hydrogen's hanging on, but oxygen's winning. I'll back up so you can see a little more in detail. All right, so if my shirt button is the center, okay, hydrogen's hanging on, but it's like almost losing, all right? We know this because the periodic table. So right here we got hydrogen, it's a little over 2, like 2.1 or so. And oxygen. Oxygen is about 3.5, or yeah, this case 3.5. Any case, the point is it's just a relative major difference in electronegativity. So the goal here is to see which atom has a bigger electronegativity. Oxygen does, so it's gonna win that tug of war. Polar bond. So bonds are polar when you have two atoms of different electronegativities. So it looks like this. Okay, it's got this bent shape. And these arrows are called dipole arrows. The dipole arrows point towards the point towards the atom that have the higher electronegativity. So, why is CO2 nonpolar when it has polar bonds? What is happening? Well, when you have the same atom on both ends, it's kind of like two tug-of-war teams pulling equally on the rope. So if we represent, like in this case, this dot's gonna be carbon in CO2. And the oxygens are just bonded to carbon like we see. And if we visualize the pulling, it's equal pulling. Notice the black dot is not moved. May have stretched a little bit, but it is not moved position like we saw with water. So, because of this, CO2 is a nonpolar molecule. There is one more scenario. You can have a nonpolar bond between two atoms, which results in a nonpolar molecule, like O2, just like this. When you have two atoms that are the same atom bonded to each other, there's no net change in like where the electrons are shifting. So the result is a zero polarity, zero polar bond, or non-polar bond. And because of that, the molecule is a nonpolar molecule. And because of all this, we see some cool properties, right? So water's a liquid room temperature, you have all this cool stuff you can do with water, and because it boils at a higher temperature than other things, CO2 and O2 are both gases at room temperature. Okay, we saw CO2 turn into a gas when we did the dry ice experiments. O2 is obviously a gas because it's floating around in the atmosphere. Now, why is O2 such a, it's way lower? It's a negative 183 boiling point degrees Celsius, as opposed to a negative 78.5 degrees Celsius boiling point. So why is that? Well, CO2's got more connecting points. So because it has more connecting points for London dispersion to happen, it's got 3 atoms as opposed to 1, and technically there's a little bit of a positive region right here. It's just hard to get to because you have these electrons in the vicinity. but it's got more connecting points or more points of contact. So it's gonna, even though the forces are weak, it's gonna be stronger than something else with only 2 connecting points. 3 is bigger than 2 by, relatively a lot. So 2 connecting points causes very little interaction, very weak interactions, which results in O2 being a gas at a much lower temperature than CO2 and way lower than H2O, our good old friend water. So, to recap, we have 3 molecules. H2O has polar bonds, and it's a polar molecule. It's got hydrogen bonding. CO2 has polar bonds, but it's a nonpolar molecule, resulting in London dispersion interactions. O2, also London dispersion, also nonpolar molecule, but it's got nonpolar bonds as opposed to polar bonds. And the boiling points all kind of result from these forces. So we see the connection between the chemical property and these physical properties that we see on the macro scale. Go eat some bagels or pasta or anything that involves water. Have a great day. Woo! All right, next up we got CO2. Woo! Okay. Every time you exhale, that's what comes out your mouth. Okay. CO2 is a gas at room temperature. It's not a liquid like water because it is a nonpolar molecule. Now, the interesting thing about CO2 is it is a nonpolar molecule, but it has polar bonds. So, let's look at this tug of war again. We have our carbon and we have our oxygen. So, same thing as water, okay? Oxygen is more electronegative than carbon. It wants electrons more than carbon. And so it's gonna pull on those shared electrons in the bond a little bit more, all right? So, we know this because on the periodic table, carbon's at about a 2.5, oxygen's about a 3.5. So, oxygen wins that fight. It's gonna pull on the bonds a little bit more. So, water looks like this. It's got dipole arrows that point towards the atom with higher electronegativity. So we have dipole arrows pointing at oxygen. And if we have a model that looks like this, it's got this bent shape because the lone pairs repel the bonds downward. Because it has this bent shape, not only does it have polar bonds, but the molecule itself is polar. And this is because one end of the molecule is negative, more negative than the other end. The oxygen is more negative than the hydrogen end, causing like an imbalance. 2 poles, like north-south, Santa Claus, okay, causing this attractive force between the 2 molecules. So water is polar, got a negative end, positive end, and they're gonna attract, kind of like this, all right? Kind of like this. Any way that the negative and positive end can interact. And this is because it's such a major win for oxygen in that tug of war, then there's gonna be an extra strong attractive force between the 2 atoms. And so that's called hydrogen bonding, a type of dipole-dipole force, intermolecular force. And I put a little star next to it because it is the strongest type of intermolecular force that we see.